Next. அவர் பேசுறது கேட்குமா? அவர் பேசுறது பேசினாலும் கேட்கணும். அவர் பேசுறது தெரியுங்களா? எப்போ முடிக்கிறாங்க? எப்போ முடிக்கிறான்னு sir. Nagar, sir. You can start now.
Dr. R. Nagarajan, Assistant Professor of English, on behalf of Science and Humanities. It is a great morning to all. It gives me great pleasure to extend to you a very warm welcome on behalf of the Department of Science and Humanities, who has clubbed all of us for the national webinar on differential equations and its applications. Encouragement, enthusiasm, excellency is one of the major aspects of the organization, with an object of encouraging the spirit of research and innovations. Feels proud to host the national webinar Differential Equations and its Applications. This event is a single day webinar specialized in specific knowledge areas. Now I invite Mrs. C.Arunmozhidevi, Associate Professor of Mathematics and HOD, Department of S&H, P.T.Lee CNCET will present the welcome address.
Good morning, one and everyone. First of all, I appreciate your interest in exploring the opportunities in the COVID-19 lockdown period by joining our online session, the national webinar on differential equations and its applications, organized by the Department of Science and Humanities, P.T.Lee Chengalvaraya Naicker College of Engineering and Technology, Oovery, Kanchipuram. In this memorable occasion, it gives me an immense pleasure in welcoming our Honorable Chairman, through Justice S. Rajeshwaran, and Honorable Trustees, Dr. M. Paramatma, Professor of Agriculture, through C. Parandaman, Advocate, through B. Sugendran, Advocate, Dr. P. Segar, MBBS, Ortho, Dr. G. Sandanam, retired IAS, through S. Tamilmani, former Deputy Director of School Education, Dr. A. Kalevani, Professor of Computer Science Engineering, Dr. G. Vishwanathan, former Vice Chancellor of Tamil Nadu Teacher Education University, Chennai. I extend a very warm welcome Dr. M. Nirmala, Assistant Professor of Mathematics, Saradha Gangadharan College, Puducherry, who has kindly consented to be the resource person for this webinar. I welcome ma'am. I heartily welcome Dr. S. Bhupati, Principal of the college, in the wonderful occasion. Next, I would like to welcome all HODs, our department faculties, and all other faculties, as well as staff members of the college. I extremely feel very proud to welcome all the participants joining from various places and from various colleges to our program. I am so happy to see you joining with us. I hope the session will be very useful and successful. And I hope all of you will enjoy the session. Once again, I welcome you all. Have a good time. Thank you very much for joining us. Thank you.
Thank you, ma'am. Next, now I ask Miss V. Bharati, Assistant Professor of Mathematics, P.T.Lee CNCET, to say the short profile of our resource person.
Good morning, one and all. On behalf of the Department of Science and Humanities, I feel very proud to introduce our Honorable Speaker, Dr. M. Nirmala, Assistant Professor at Saradha Gangadharan College, Puducherry. Dr. M. Nirmala was awarded PhD in Mathematics at Pondicherry Engineering College during this year 2015 to 2020 with the title Contribution to the Study of Batch Arrival Bulk Service Non-Markovian Queuing System with Unreliable Server and Multiple Vacations. She was awarded MPhil in Mathematics at Kanji Mamunivar Center for Postgraduate Studies during this year 2001 to 2002. She was awarded MSc in Mathematics First Class with Distinction at Kanji Mamunivar Center for Postgraduate Studies during this year 1999 to 2001. And also she won Regis Gold Medal during the year 2001 at MSc. She was also awarded BSc in Mathematics First Class with Distinction at Bharatdasan Government College for Women, Puducherry during this year 1996 to 1999. She also qualified state eligibility test. Dr. M. Nirmala is serving as an assistant professor at Saradha Gangadharan College, Puducherry. She is a committed teacher and has 13 years of teaching experience in various colleges in the UT of Puducherry. She began her teaching career in the year 2002. Her areas of research include probability, random processes, and queuing models. She has published research articles in reputed national and international journals. Thank you.
Thank you, ma'am. It is my privilege to invite Dr. M. Nirmala, Assistant Professor at Saradha Gangadharan College, Puducherry, to share her views and knowledge about the national webinar on differential equation and its application. Welcome, ma'am. Now, I handed over this session. I handed over this session to you, ma'am. You can proceed, ma'am. Ma'am.
Thank you, madam. Thank you, madam.
Okay, ma'am. Thank you, ma'am.
Happy morning to all of you. I am Nirmala, Assistant Professor, Department of Mathematics, Saradha Gangadharan College, Puducherry. At this juncture, I would like to express my sincere thanks and gratitude to the Principal, Head of the Department of Science and Humanities, and the conveners of the webinar of P.T.Lee, Chengalvaraya Naicker College of Engineering and Technology, Kanchipuram, for giving me an opportunity to conduct the webinar on the topic Differential Equation and its Applications. I welcome professors, staff members, and students of P.T.Lee Chengalvarayan College of Engineering Technology for this presentation. I also extend my warm welcome to all the teachers, students of various colleges for their inquisitive interest in learning mathematical concepts. Welcome you all. In this webinar, we are going to see about differential equation and its applications. The contents, first we are going to see about a brief introduction, definition and terminology, formation of ordinary differential equation, solution of ordinary differential equation, types of differential equation and its solution, applications of ordinary differential equation, numerical methods to solve ordinary differential equations. Introduction. Many physical problems, when formulated in mathematical forms, leads to differential equations. Excuse me. Many of these problems are complex in nature and very difficult to understand. When they are described by differential equations, it is easy to analyze. So, we have to have an in-depth study of differential equation, which has assumed a prime importance in all modern scientific investigation. Differential equations have variety of applications in physics, chemistry, biology, anthropology, geology, economics, etc. What is meant by a differential equations? Since many of the students, staff members are attending this webinar, I will start from some basic things. So it will be useful for all. So differential equation is basically an equation which involves one or more independent variables, a dependent variable, and one or more differential coefficients. Here, this is the symbolic representation of differential equation. Here I consider x to be the independent variable, y to be the dependent variable, dn y by dx power n. This is the differential coefficient of the dependent variable on independent variable, and c is a constant. So symbolically, I can represent a differential equation by this one, containing independent variable, dependent variable, its differential coefficients with constants. We can classify the differential equation based upon the type into two, ordinary differential equation and partial differential equation. What is meant by differential equation, ordinary differential equation? A differential equation containing only one independent variable, that is, a differential equation involving derivatives of the dependent variable with respect to only one independent variable is called an ordinary differential equation. In the example, we can see y is the dependent variable. It depends on a single independent variable. So this is an example for an ordinary differential equation. D square y by dx square minus 5 dy by dx plus y is equal to 0. This is also an ordinary differential equation. Here, y is the dependent variable, depends on a single independent variable. Since this is an ordinary differential equation, we use the notation D. Next, partial differential equation. What is meant by partial differential equation? A differential equation involving derivatives with respect to more than one independent variable. That is called partial differential equation. You see here in the first example, u is a function of x and y. U is a dependent variable. It depends on x as well as y. Here x and y are two independent variables. So in the second example, z is a function of x and y. Z is a dependent variable, depends on x as well as y. So in this differential equation also, we can see there are two independent variables. So therefore, if any differential equation possesses more than one independent variable, we call it as partial differential equation. Here the notation instead of d, we are using dou. Dou by dou x, dou by dou y, dou square is by dou x square, dou square is by dou y square. I think it is clear. Next, we see order and degree of a differential equation. What is an order? In a differential in an equation, the highest differential coefficient of the dependent variable with respect to independent variable involved in a differential equation is called the order of the differential equation. That is, in a differential equation, we have to see what is the highest differential coefficient. That gives the order of the differential equation. We'll see in examples. The power of the highest order derivative involved in a differential equation is known as degree. See, we already know the order, the highest differential coefficient. That power, the highest differential coefficients or power of that one or exponent of that one gives our degree. For finding degree, we should be very careful whether the differential equation is in the polynomial form. Otherwise, the degree of certain differential equation cannot be formed. So you have to check whether the differential equation is in polynomial form. Then only the degree can exist. We will see. Order and degree should be a positive integer. That is very important. It should not be a negative integer or it should not be any fractions. In first example, you see dy by dx the whole cube minus 4 dy by dx plus y is equal to 3 e power 2x. This is an ordinary differential equation. Here the highest differential coefficient is dy by dx, that is d by dx of y. So it is of order 1. So this is a first order differential equation. So this is of order 1. Order 1. The highest coefficient is 3. Therefore, its degree is, the order is 1. Order is 1. The power of the highest order is 3. Therefore, degree is 3. The second example, you see d power 4 y by dx power 4 the whole power 2 by 3 is equal to dy by dx plus 5. You see the order is, you can easily find it is 4 because the highest differential coefficient is of order 4. So the order is 4, but this differential equation is not in a polynomial form. You just remember what is meant by a polynomial. Any polynomial, example, a naught x power n plus a1 x power n minus 1 plus a2 x power n minus 2, etc. Here, x power n, if it is a polynomial, that n should be a positive real number. It should not be a negative number. It should not be a fraction. Therefore, here also, we should confirm the differential equation is in the polynomial form. Since there present a fraction, it is not possible to find the degree for this one. So better you try to convert in form of a polynomial. So in order to change that one, I am taking a power that is rising to the power on both sides. What happens, you see? d4 by dx power 4, 2 by 3 the whole cube. The same I have to take for the right hand side also. dy by dx plus 5 the whole cube. This 3 cancel out. So d power 4 y by dx power 4 the whole square is equal to dy by dx plus 5 the whole cube. In this differential equation, you see this is the fourth order differential equation because the highest differential coefficient is d power 4 by dx power 4. The power, the exponent of this higher order is 2. Now you see, now this differential equation is free from radicals, that is the power, fractions, there is no fraction, there is no negative number. So now I can state this differential equation is of order 4 and degree 2. Is it clear? Third example, d cube y by dx cube is equal to tan dy by dx. This differential equation is not in a polynomial form. Why? A polynomial equation should be free from tan, sine, log. But here differential coefficient comes under tan. So this differential equation is not in a polynomial form. I can find the order for this one. This is of order 3. But the degree is not possible to find. Therefore, this differential equation has no degree, or I can say the differential equation, the order for this degree for the differential equation is not defined. Clear? See the fourth example, dy by dx is equal to root of 2x minus 3 plus sine y minus log 2x. You can ask me, in this differential equation also, sine function is there, log function is there. Is it possible to find the degree? Yes. This equation is in polynomial form. Is it clear? You see, what is the difference between these two, example 3 and example 4? In example 3, the derivative comes under tan. But here the derivative is free from sine, cos or tan. So derivative is in polynomial form. I'm not bothered about some y term or x term which comes under log or sine. It doesn't affect this polynomial differential equation. So therefore the derivative is a first order. Therefore the order is 1. The power of this first order is 1. Therefore the degree is 1. Is it clear? So we should be very careful. We should be concerned that the differential coefficients are free from polynomials. That is very important. That isn't in polynomial. So these are the basic things I want to share with you about differential equations. Now, in many of the practical situation, how to form a ordinary differential equations. You know, as a mathematical student, everybody know how to solve an ordinary differential equation. As engineering students, you have many situations where your situation you have to convert in terms of a differential equation. Then automatically it can be easily solved. We have lot of methodologies to solve. The thing is, you should know how to express situations given for you in terms of differential equation. So I take very simple problem, easy to understand, to convert to make a differential equation. In example 1, you see a population growth at a rate of 4% per year. If y of t denotes the number of individuals in this population after t years, then the rate of change of y is equal to 4% of y. The rate of change that denotes the derivative. Any rate of change of any object with respect to time or any other media gives our derivative. You see here what is given. If I take y of t is given to be the number of individuals in the population at time t. The rate of change of y with respect to t is written as dy by dt. That is what is said, they is equal to 4% of y. 4% means 4 by 100 of y. So it's a very simple differential equation. From this statement, I frame a simple differential equation. dy, the rate of change of y with respect to time t, is equal to 4% of y. Clear? Second example. A saving account pays 6% interest per year, compounded continuously. In addition, the income from another investment is credited to the account continuously at a rate of rupees 500 per year. Form the differential equation. The situation is given, a saving accounts, they are paying 6% interest per year. Now, additionally, at a rate of 500, the money is added to that account. So, yeah, you should take one function y in terms of t, which depends on t. Here, the independent variable is t, dependent variable is y. Y, the income, the saving account depends on time. So, if y is equal to y of t denotes the amount in rupees in the account after t years, then the rate of change of money with respect to time is equal to 6%. So, 6 by 100 of the money rate plus additional amount of 500 is added each year. So I have to add 500. So this situation is framed uh, um, explicitly in terms of a first order differential equation. Is it clear? So dy by dt represents the rate of change of the income, the money in the account, which is equal to 6% of y plus 500. The next example. So consider a mass hanging from a stretched spring. The force on which a mass is proportional to the position y. Okay, so the force is equal to, the force is always proportional to the position. If I consider the position of the particle as y, then the force is equal to the proportionality constant. I am taking k into y. Why I am putting minus k? Since it is against the gravitation, so minus sign will be there. So this is a simple equation framing for the given situation. By Newton's second law, we know that force is always equal to mass into acceleration, ma. Force is always equal to m into a, mass into acceleration. Now F is equal to ma. If I substitute in the previous equation, I get ma is equal to minus ky. Here a is nothing but rate, that is acceleration. The rate of change of position is called velocity. The rate of change of velocity is called acceleration. Therefore, m d square y by dx square is equal to minus ky. So this is the differential equation framed for this given situation. Here you see, if I solve this differential equation, I got the answer in terms of sine and cos. Sine and cos is a wave function. So automatically, the solution of this differential equation involves sine and cos. So the mass hanging from a spring will oscillate up and down, where there will be a wave function. On seeing the equation itself, we can say which represents a situation given above. So it is a mass hanging from a stretched string. The force is proportional to the position. So I framed the equation. By Newton's second law, I framed a second order differential equation. Since its solution contains sine and cos, the mass hanging from a spring will oscillate up and down. It's clear. Now, for the past three examples, we see a simple situation is given for that how to frame a differential equation. Now, equation is given how to frame a differential equation for any equation in terms of x. Here x is given to be a cos nt plus alpha. So if I want to frame a differential equation, we should be careful that I can differentiate this equation as many times as there are number of arbitrary constants. If there are one constant, I have a freedom to differentiate only once. If I have two constant, I can differentiate up to two times, not more than that. Here, x is equal to a cos nt plus alpha. Here, a and alpha are the only two arbitrary constants. So, if I want to frame a differential equation, I can differentiate for two times only. Okay, so x is equal to a cos nt plus alpha. I'm differentiating once, I'm having minus na sine nt plus alpha. If I differentiating one more time, d square x by dt square is equal to minus n square a cos nt plus alpha. If I'm replacing here, so our aim is to eliminate the constant. So a cos nt plus alpha can be replaced by x. So I'm having d square x by dt square is equal plus n square x is equal to 0. So we have a second order differential equation. Is it clear? So one thing you should remember, if I want to frame a differential equation from any equation, I have to differentiate as many times as I have the number of constant. If there is one constant, I have a liberty to differentiate only once, not more than that. If I have two constant, I have a liberty to differentiate twice, not more than that. Within that, some you have to frame the differential equation. Some we can use the given equation also. Here also I'm using the given equation. Then only this constant can be replaced. Therefore, you have to remember this idea if I want to frame the differential equation. Clear? Now, one more thing. Here, the situation is given I have to frame the equation and then I have to frame the differential equation also. Form the differential equation of family of circles touching the x-axis at origin. Family of circles touching the x-axis. So if a concentric circles, not only a single circle, we are having family of circles. Suppose C denotes the family of circle touching the x-axis at origin, then automatically the center of the circle will be 0, e. A may be any number, any arbitrary constant. A may be 1 for the first circle, A may be 2 for the second circle, A may be 5 for the third circle, etc. So A is a only arbitrary constant here. Then automatically what will be the radius? A is the radius of the corresponding circles. Therefore, any circle with center 0, a and radius a can be represented like this. X square plus y minus a the whole square is equal to a square. On simplification, I am having x square plus y square is equal to 2ay. Remember, this equation having only one constant a. A is a only arbitrary constant. So if I want to frame a differential equation, I have a liberty to differentiate only once. Okay. So if I differentiate the equation, I got x plus y dy by dx is equal to a dy by dx. From this equation, I take the a value. So a value is nothing but x plus y dy by dx by dy by dx. So I'm replacing this a value in the first equation, and after simplification, I got the value. So if I replace here, I got dy. After further simplification, we get dy by dx takes the form 2xy by x square minus y square. This is the required differential equation of the given family of circles. So this is the required differential equation of given family of circles. So now for the past few slides, we know how to frame the differential equation, how to, if the equation is given, how to frame the differential equation. If the situation is given, how to frame the differential equation. Now, we are going to see certain um, methodology to solve the first order differential equations. The first simple method is variable separable method. Variable on seeing the statement itself, I am going to split into variables. dy by dx is equal to f of x comma y. dy by dx is equal to f of x comma y. Here f of x comma y, if it is possible, into split into two functions, p of x and q of y. P of x is purely a function of x, q of y is purely a function of y. So if it is possible to split f of x comma y in terms of p of x and q of y, then I can split this variables into two. As completely I frame y term separately and completely x term separately, I can integrate. If it is possible to split it like this. If it is not so, we cannot do. If it is possible, the right hand side of the differential equation in terms of x and y, I can separate into two different groups. So dy by q of y is equal to p of x into d of x plus c. So based upon this variable separable method, we are going to see one example. The marginal cost of manufacturing a certain item is given by dm by dx, which is equal to 2 plus 0.15x. Find the total cost function m of x, given that m of 0 is equal to 100. Usually economists use the word marginal cost for the first derivative usually. So this problem is based upon this. You see dm by dx is equal to 2 plus 0.15x. Here the independent variable is x, the dependent variable is cost function m. M depends on x. Here, if it is possible to split m and x separately, then I can apply variable separable method. Now, here the right hand side is free from m, so I can split easily into two groups containing m as well as x. So integration of dm is equal to integral 2.01.5 x dx plus integrating constant. So on integrating m, we get m of x. On integrating 2, we get 2x plus 0. If I integrating x become x square by 2. So on dividing, I got 0.075 x square plus integrating constant. In this situation, I want to tell one thing. Your differential equation, the solution of a differential equation containing the arbitrary constant is said to be a general differential equation. If I found this constant value and the solution is free from arbitrary constant, that is called the particular solution. There are two types of solution, general solution and particular solution for any differential equations. A differential equation with arbitrary constant is called as general solution. A differential solution for a differential equation free from arbitrary constant is called particular solution. Here, this particular solution can be got only if they given any information. That is, we call it as initial condition. If the condition is given, I can found the value of any arbitrary constant and then replace it. That gives our particular solution. Now you see, m of x is equal to 2x plus 0.075 x square plus b. Here a is the arbitrary constant. So m of x is our general solution. Here the initial condition, one information is given. M of 0 is equal to 100. That is, m of 0 means at x is equal to 0, the marginal cost value will be 100. So I'm going to use this condition to find the arbitrary constant. So I'm replace x by 0. M of 0 is equal to 100. From this, I found the value a to be 100. Therefore, m of x takes the form 0.075 x square plus 2x. Instead of a, I'm replacing by 100. So the last equation is a particular solution for the given differential equation. Is it clear? So for a differential equation, there are two types of solution. A solution containing arbitrary constant is called the general solution. A solution containing that is free from arbitrary constant. Using some initial condition, if I found that arbitrary constant and replace the constant, I get a solution which is free from arbitrary constant. That is called particular solution. Now, a very good example, Newton's law of cooling. So this also this situation also, this law also we have to frame it in terms of a differential equation. Let's say, according to this law, the rate at which the temperature of the body decreases is proportional to the difference of the temperature between the body and its environment. That is, the temperature of the body decreases proportionally to the difference in the temperature. So D, if I take theta to be the temperature, then the rate of change of temperature with respect to the time is equal to proportional. So I put a proportionality constant K, difference between the temperature. Theta is the temperature of the body, theta E is the temperature of the environment. So the difference is theta minus theta E. Why I put minus here? Since it is decreases, they represent the decreasing thing and put minus here. K is always a positive number. So this situation is framed in terms of a simple differential equation. D theta by dt is equal to minus K theta minus theta E. Theta is the temperature of the body. Theta E is the temperature of the environment. K is the proportionality constant. Here also this differential equation can be easily split, group into two in terms of theta and in terms of t. So I am grouped the theta terms one side and put d theta by theta minus theta e, which is equal to integration of minus k dt. So the integration of this term leads to log ln of theta minus theta e, which is equal to minus kt plus c. So this is a solution. This is a general solution since it possesses arbitrary constant c. So so if I want to simplify more, taking exponential on both sides, so we get theta is equal to theta e plus c e power minus kt. Here theta is the temperature of the object. Now you see, this is the graphical representation. The theta decreases, but it anyway it's not coincide with theta e. As t increases, as t tends to infinity, the theta is decreasing towards this one, but anyway it is not coincide with theta e. So this is a graphical representation of this solution. I think it's clear. So in this example, Newton's law of cooling, the situation is the temperature of a body decreases is proportional to the difference of the temperature between the body and its environment. This can be represented in terms of this differential equation. So this can be grouped into two. Therefore, I apply variable separable methodology to solve this equation. So the solution is like this: theta is equal to theta e plus c e power minus kt. This function decreases exponentially but approaches theta e as t tends to infinity instead of 0. At last, it is approaching to theta e as t tends to infinity. The next very interesting example is maxima minima in differentiation. That is, we know everybody, I think, have a basic idea of maximum minima. What is maximum value? What is the minimum value? When a function attains its maximum value or minimum value. So necessary condition is, in order to attain its maximum or minimum, the necessary condition is the first derivative of the function with respect to the independent variable should be 0. The sufficient condition is dy by dx is equal to 0. Also, the second derivative should be less than 0. That is, d square y by dx square is less than 0. If it is so, then we can call the function attains its maximum. Suppose d square y by dx square is greater than 0, then I can say the system or the condition y attains its minimum value. So these two are the criteria for maxima and minima. Using this condition also, we can solve differential equations. You see this example. The total cost and total revenue of a textile industry is given by C is equal to x square minus 12x square plus 48 plus 11 and R is equal to 83x minus 4x square minus 21. This is the total cost and this is the total revenue. Find the output when the revenue is maximum, when the profit is maximum. So we are in a position to find the value of x here. That is the output. When the revenue is maximum, what will be the value of x? When I want the profit to be maximum, what will be the value of x? This we are going to find. So for this, I first took the revenue. R is equal to 83x minus 4x square minus 21. This is the revenue equation. I am differentiating with respect to x. So dr by dx, I am taking 83 minus 8x. I go for the second derivative, I got minus c. So I want the revenue to be maximum. I am going to check whether the second order derivative is less than 0 or greater than 0. For that, I equate the first order derivative dr by dx to 0. Dr by dx is equal to 0 and d square r by dx square should be less than 0. Then only I can say the revenue is maximum. While equating dr by dx is equal to 0, I got 83 minus 8x is equal to 0. Therefore, x is equal to 83 by x. Now, substituting the x value in d square term, I get a negative value minus a, which is less than 0. So, therefore, dr by dx, if I equate it to 0, I got a x value. If I substitute this x value in d square r by dx square, I got a negative value that is less than 0. This satisfies the condition for maximum. Therefore, the revenue is maximum if I take the output as 83 by 8. Clear? Therefore, when the output is x is equal to 83 by 3, then the revenue will be maximum. Now, they are also asking when the profit will be maximum. Profit is what? The revenue minus the cost. So they didn't give directly the profit. So we have to frame the profit by subtracting revenue minus C from revenue. That is, the revenue is income, the cost is expenditure. R minus C always gives our profit. So find the profit value. Now differentiating this P with respect to X and find the second order derivative with respect to X and take the values. So if I want the profit to be maximum, dP by dx should equate it to 0 and d square by dx square should be less than 0. Is it so? So the profit is maximum by equating dP by dx is equal to 0, d square by dx square less than 0. If I equate it to 0, I got two values for x, minus 5 by 3 and 7. These are the two outputs I got when I equate dP by dx as 0. So I take x is equal to minus 5 by 3 and put it in d square p by dx square. I got the value as 26, which is greater than 0. Similarly, if I put x is equal to 7 in d square by dx square, I got minus 26, which is less than 0. So When I put x is equal to minus 5 by 3, the second order derivative is greater than 0, therefore p will be minimum. If I put x is equal to 7, I got a negative value which satisfies the maximum condition, maximum criteria. So it is less than 0, therefore p is maximum. So I have to choose x is equal to 7 in order to maximize my profit. So this is the way you have to proceed for using maximum minima. So maximum minima is a wonderful concept in differentiation to check the maximality and minimality of the any situation, that is any objects. Now, so after this few slides, we see how the first order differential equation are solved by variable separable method and what is the practical application for applying the derivatives, first and second order derivatives. Now we are going to see applications of linear differential equation. A very good example is simple harmonic motion. Simple harmonic motion results in a linear differential equation. We will see. When a particle is said to execute a simple harmonic motion, if it moves in a straight line such that its acceleration is always directed towards a fixed point in that line and is always proportional to the distance of the particle from the fixed point. It's clear. If O is considered to be the fixed point of the line A dash, O is the fixed point. P is the position of the particle at any time t. Then the distance between O and P is x. Since the acceleration is always directed towards O, the acceleration is always directed towards O, pulling towards O. So it is a direction opposite to of the x. Is it clear? O is the fixed point. P is the position of the particle at any time. So OP distance I consider to be x. Since the acceleration is always directed towards O, the direction is opposite to that of x. So with this in the mind, I'm going to frame the differential equation. Okay. d square x by dt square is equal to minus lambda square x. Here x is the distance. So the rate of change of position, first is velocity. Then d square x by dt square gives our rate of change of velocity, which gives our acceleration. That acceleration is equal to minus. So it is in the opposite direction of x. So I put minus lambda square x. Lambda square is nothing but a constant. In order to solve easily, I put lambda square. We can put any constant, but you get the answer will be in terms of root. In order to avoid that, I put lambda square x. So the acceleration is minus of the constant, proportionality constant into x. This minus sign is due to this is in the opposite direction of the displacement. Is it clear? So this is a linear second order differential equation. So this type of equation can be solved by framing. First, you have to frame the auxiliary equation. Then go for the particular solution. This type of equation has two solutions, complementary function and particular integral. Any linear differential equation have two solutions, that is complementary function and particular integral. So in order to find the complementary function, first you have to frame the auxiliary equation. What is auxiliary equation? You have to replace this d, the differential coefficient, by some m value plus lambda square is equal to 0. While solving, I get m is equal to plus or minus I lambda. So this depends upon the root. We have 4 types of complementary function. Here I'm not going deep into that. For this situation, I'm going to tell. Okay. Here I'm having a complex root, that is 0 plus or minus I lambda. If I got such a root, the complementary function takes the form e power alpha x. Here there is no x coordinate. So e power 0x becomes 1. A cos lambda t, that is beta t. A cos lambda t plus b sin lambda t. So this is the complementary function for this differential equation. Since I am getting a complex root, this is the complementary function for our differential equation. So x is nothing but the distance. The rate of change of displacement gives our velocity. So I simply differentiate with respect to t. So a cos lambda t gives minus a lambda sin lambda t. Sin lambda t gives b lambda cos lambda t. So x is the displacement and this is the velocity. So already I told you this is a solution, but this is the general solution because we are having two arbitrary constants. So in linear differential equation, to eradicate this constant, we should have some initial conditions. They, in some problem, they will give explicitly the initial condition. For this problem, we have to take our initial condition from the given situation. Yes. Here, at time t is equal to 0, the distance will be x. That is, the particle is at rest. So at the starting point, x will be a. Using this condition, at t is equal to 0 and x is equal to a, if I put it in that equation, I get capital A value to be a. At t is equal to 0, similarly, at rest, the rate of change of displacement, that is, the velocity is always 0 because the particle is at rest, there is no velocity. Then dx by dt is also equal to 0. Therefore, using this condition, I got the value b to be 0. Now I got a and b value. So substitute these two values in x and dx by dt. Now our equation is free from arbitrary constant. So x is equal to a cos lambda t and dx by dt is equal to minus a lambda sin lambda t, represent the displacement and velocity of the particle at any time t. Is it clear? So this example is very interesting example. A simple harmonic motions. Here, a simple harmonic motion is converted in terms of linear differential equation. So a very good application of linear differential equation we can see in simple harmonic motion. Next type of equation is homogeneous equation. So this is also a linear equation. Dy by dx, the right hand side will be a function of x and y. You already seen that as variable separable method. If the right hand side is possible to separate into variable and separable, then I can frame. If it is not so, I have to check whether it is homogeneous type. If it is homogeneous means it should be in the ratio, that is said to be homogeneous, does not depends on x or y separately, but depends on the ratio y by x or x by y. Therefore, dy by dx is equal to some function of y by x. So in such a situation, we cannot solve directly this method. We have to use some substitution. Here, I'm using the substitution y is equal to vx. Then dy by dx will be v plus x dv by dx. So if I use the substitution y is equal to vx and dy by dx is equal to v plus x dv by dx, then this particular equation, this homogeneous equation, converted to a form of variable separable method. Then we can know how to proceed and solve. Is it clear? So this type of equation also have a wide applications in engineering as well as in many fields. So up to this, we see a linear differential equation and first order differential equation and its application. In the remaining slides, we are going to see what are all the different types of linear differential equations we have and how to solve it. A brief introduction about that one I'm going to give. A standard form of linear equation of the first order is commonly known as Leibniz linear equation, which will be in the form dy by dx plus py is equal to q. Here p and q are functions of x alone. P and Q are functions of x alone. If this type of equation is given, then its solution will be in the form y integrating factor is equal to integral of q into integrating factor. You have to integrate with respect to x plus c. Here the integrating factor can be calculated by e power integral p dx. So this is a solution for this type of linear Leibniz equation. So if a differential equation of this form, I have to use this methodology to get the solution. The other important solution is Bernoulli equation. This is of the form dy by dx plus py is equal to q y power n. Right hand side you see q y power n. So this cannot be solved easily. So I have to convert or reduce to Leibniz form. If it is possible to reduce to Leibniz form, it can be easily solved by the previous method I explained. No, you have to frame the integrating factor and use that methodology to solve Bernoulli equation. Then The another important differential equation is Clarets equation. The equation of the form y is equal to px plus f of p is called Clarets equation. Here p is nothing but our differential coefficient dy by dx. So this equation, this type of equation is also widely used. This can be also solved by some manipulation to convert in terms of Leibniz equation. The next important differential equation is exact differential equation. The exact differential equation is of the type m of x comma y dx plus n of x comma y dy is equal to 0. Here m of x comma y is a function of x and y. N is also a function of x and y. First you have to check whether it is in exact form. That is, you have to check for the thing dou m by dou y is equal to dou n by dou x. If this condition is satisfied, then I can call this differential equation is of exact differential equation. If it is exact, the solution will be in this form: integral m dx plus integral terms of n not containing x dy is equal to c. That is, m dx, if I want to integrate m dx, you should treat y temporarily as a constant. You have to treat x as constant and then you have to integrate. Then in the second integral, I have to integrate n only the terms not containing x with respect to y. Here m we have to integrate with respect to x. Here n I'm going to integrate it with respect to y. I have to take the terms not containing x, which is equal to c. So this is the solution for an exact differential equation. So any general linear differential equation of nth order will take this form: d power n y dx power n plus p1 dn minus 1 y by dx power n minus 1 plus p2 dn minus 2 y by dx power n minus 2, etc. p and y is equal to x. This is a general linear equation. So here p1, p2 are all functions of x. Also the capitals also functions of x. So a general differential equation of nth order with constant coefficient will be this form: dny by dx power n plus k1 dn minus 1 by dx power n minus 1 plus k2 dn minus 2y by dx power n minus 2, etc. k and y is equal to x. Here p1, p2, pn are all functions of x, but here k1, k2 are all exactly constant. So this is a general linear equation of nth order with constant coefficient. This equation have a solution of the form y is equal to complementary function plus particular integral. In previous slide, I explained one model, that is where complementary function and particular integral exists. If the right hand side is any function not 0, then we get a particular integral. Only the complementary function can exist for certain differential equations. So any general differential equation of nth order with constant coefficient can be evaluated and its solution will contain two functions: complementary function and particular integral. This linear differential equation of nth order or any order is have a wide applications in engineering fields. There are few ordinary differential equations cannot be solved by the previous methodology we discussed. We have a lot of method: variable separable method, homogeneous equation, exact equation, linear equation of nth order, etc. etc. There are few differential equations which cannot be solved by these methods. Then we have to go for numerical methods of solving. There are lots of numerical methods which gives a exact solution for that differential equation. That is Picard's method, Taylor's method, improved Taylor's method, Euler method, Runge's method, Runge-Kutta method of higher order, that is second order as well as fourth order. Runge-Kutta order of fourth order also is there. Predicted corrector method, Adams-Bashforth method. In predicted corrector method, if I want to apply and all, we should know some previous values. Then only we can do. So that previous values can be calculated by Taylor's method, Euler's method, etc. And then I go for predicted corrector method. Adams-Bashforth method is also a wonderful method to calculate the ordinary differential equation numerically. Is it clear? So there are few ordinary differential equation cannot be solved using the previous method. We go for numerical solution. These methods are very useful to get the solutions. Thank you. So, in the full webinar, we discuss what is meant by ordinary differential equation, how to express the ordinary differential equation in terms of, that is a situation in terms of ordinary differential equation, and solution of the ordinary differential equation by various methodology and numerical solutions. Thank you for your listening.
Thank you, ma'am.
Thank you, madam.
Thank you. This session was very informative and helpful to all of us. Thanks a lot, ma'am.
Thank you, madam.
Some of the participants raised the questions about this webinar in chat box, ma'am.
Sure.
Shall I ask?
Okay, madam. Okay, madam.
One participant asked, can you explain how difference equation helpful for engineering, particularly in analysis? How can you explain how difference equation helpful for engineering, particularly in analysis?
Yes, a differential, that is in a engineering field, many situation can be framed into, already I told you, many situations in your problems can be framed into differential equation. If you know the technique of representing your situation in terms of differential equation, then you can apply various methods. We have discussed various methods. No, you can apply it and get the solution. The only thing is you should know the technique of representing your situation in terms of differential equation. If you represent it in differential equation, that whatever problem, it can be easily solved. So you can easily get the solution for that. Okay, it's clear.
Okay, ma'am. Next,
Okay.
next one of the participants asked, please give information of differential equation related to research field. Please give information of
Research.
differential equation related to research field.
We can have, there are many differential equations cannot be solved. There are many unsolvable problems also there in differential equation. You take that differential equations and try to solve it by any methodology. There is a lot of methodology you go for. There is a lot of technical website is also there. You can apply MATLAB, lot of things. If you have interest, you take that unsolved problems and you applied any of the techniques and any of the mathematical technique or some numerical solution also you can get. So you apply it, you try it. There is a lot of papers. You can, it will be very useful for you. If you found such equations, it will be very useful for others also. So search for such equations and try to solve it. Okay, that is the research. You can get lot of papers. If you go for online, if you go for Google search also, you can get lot of unsolvable ordinary differential equations.
Okay, ma'am. Thank you, ma'am. Thank you
Okay.
very much. Now we will conclude this session with vote of thanks.
Okay.
Thank you, madam, for these opportunities. Good morning to all. I deem it a great honor to propose the vote of thanks to our management, P.T.Lee Chengalvaraya Naicker Trust, has helped us in making this webinar such a resounding success. First of all, I would like to propose hearty vote of thanks to our resource person, Professor Dr. Nirmala, for making excellent presentations and making this webinar interesting and meaningful. I would like to express our profound gratitude to our principal, Dr. S. Bhubadi, for his support to this webinar. I am happy to express special thanks to our HOD and convener of this program, Professor C.Arunmozhidevi, for arranging this wonderful webinar in our department. I would like to thank co-convener, coordinator, co-coordinators in our department for this webinar great success. I am also thank to Professor Dr. R. Nagaraj, Professor E. Kamalnathan, and Mr. V. Balamurugan for their technical support. Finally, I thank to all the participants in our program. Thank you.
Thank you, Andendon, for attending my presentation. Thank you. Can I leave, madam?
Okay, ma'am. Okay, ma'am. Thank you, ma'am. Thank you.
Okay. Thank you. Thank you, madam.